Excellent. So welcome to the third session of the ArduPilot 2022 Dev Conference. And this evening, we've got a great lineup of speakers. So we're starting with Andy Palmer and Matthew Hampsey, who are talking about ArduPilot Aerobatics. Over to you, Andy.
Well, Trich, thank you very much. And thank you for inviting us to talk about this exciting development for ArduPilot. ArduPilot, well, I guess specifically ArduPlane Aerobatics. My name's Andrew Palmer and I'm based in Christchurch in New Zealand. I thought given this conference is hosted out of Australia, it would be remiss not to mention some trans-Tasman rivalry. New Zealand and Australia have got a long history of sporting competition between the two countries, and that includes radio control aerobatics. So my photo here shows the New Zealand 2019 Trans-Tasman aerobatic team. The photo was taken in Tin Can Bay in Queensland at their model club there. And this was just after New Zealand won the 2019 Trans-Tasman aerobatic competition. Now, I should say that it's actually rather rare that New Zealand wins this event on Australian soil, but nevertheless we did. And I was fortunate enough to take away first place individually.
Fantastic.
So I'm going to start by talking about why my interest in autonomous aerobatics and a little bit about how I sort of headed down the path of trying to achieve this and our first steps and first flights. And also, as we discovered, the need for changes as things have been developed. And then Matthew's going to talk about the implementation of quaternion navigation and our upcoming milestones. So, autonomous aerobatics. Well, in the full-size world, in 1913, a military pilot by the name of Nesterov was the first in the world to perform a closed curve in a vertical plane. Basically, he did a loop. And with this maneuver, Nesterov really laid the foundation for modern aerobatics. Of course, the aerobatics in the model world means different things to different folks. We talk about precision aerobatics, which I guess is a bit like figure skating. IMAC, which is a little bit more like, I guess, slalom skiing. And freestyle or 3D aerobatics, and I guess I'll use my winter sport analogies, is like snowboarding. And of course, to some pilots, though, aerobatics is simply doing the occasional loop or the occasional roll. So adding aerobatic possibilities to ArduPilot gives pilots using ArduPilot something really cool to show their mates, but there are also potential uses in collision avoidance and upset recovery and other more serious applications. But my interest in this was something a little bit different. So a little bit of background. I've been flying model aircraft, aerobatics, and in fact full size for a long time. I did some recent work as a rescue pilot for a company using an autonomous autopilot system. And that was really my first introduction to autonomous systems for model aircraft. And I thought, well, it would be quite fun to give ArduPilot a try myself. Now, concurrently, a group I was involved with were developing a system for displaying competition aerobatic flights as a ribbon or a trace on a computer screen, with eventual thoughts towards autonomous judging. And I thought, well, it would be really cool to have a model fly the competition maneuvers autonomously, so we could actually see what the perfect schedule should look like in real life, because it's all very well seeing a model fly a ribbon on a computer screen, but you actually need to know what should it look like in real life. And so that was really my trigger point for the interest in autonomous flight. And this would be great, not only for pilot training, but also for judge training as well. But I thought, well, a good starting point would be, could I get a model to fly the outline of the aerobatic box? So for precision aerobatics, the schedule's flown in a defined area of 3D space called the aerobatic box or aerobatic zone. This area of sky is 150 meters out from the pilot. It's bounded from center, 60 degrees either side of center, and has a height limit also of 60 degrees. And I wondered, well, could we fly this path autonomously? And I quickly discovered, well, no, it's not really possible with the current code. So this is a quick render of what I was trying to achieve. So you can see the aircraft here flying along at baseline height, maybe 50 or 60 meters altitude, going up one end of the box, climbing to the top of the box, flying inverted back to the other end, and then a vertical downline and exiting out the bottom. So that's not an aerobatic maneuver in its own right, but that was just what I wanted to start to do, which was to show the judges and show myself as a pilot the bounds of the aerobatic box when you're standing at pilot position. Eventually, this is the sort of thing I'd like to do. So this is the F23, so the Fai Aerobatic Sequence. It's a bit of a jumble of lines on the screen, but there are lots of loop roll elements in there, a few snap rolls and spins and bits and pieces, but basically it's all about loops, rolls and straight lines. And I'm hoping one day we might be able to do, if not all of that, at least parts of it. So how was I going to achieve this? Well, it was clear just from my early reading that Arduino in its current form would not really get me upside down. Now, my mother took my brother and I to night school classes in BASIC in the early 80s, but that's about it. I'm not a coder. I bumbled my way through an iOS and Android app, but nothing more. So really I was a bit lost and not quite sure where to go. But in my Google searching, I stumbled across the Aerobatics commercial support page, and I saw Andrew Tridgell as a lead developer and thought, well, an email to him would be worthwhile, nothing lost. So a week or two went by and really I'd about given up all hope, but then a reply arrived. Andrew said, sounds like a great project. So it put a smile on my face and we were underway. So I met up with Tridge on Discord and he very kindly spent a lot of time talking me through the Arduino code base, how things worked, and thought that using a Lewis script to implement a mission item or a script item during a mission and returning back to the mission would be a good place to start. So Tridge added a new mission script item, made the required changes to the C++ code, and very quickly we had a scripted loop where we could set the roll rate to 0, define a pitch rate, define a throttle percentage, and away we went. And we could do a roll in a similar manner. But early on, we discovered that we'd need a yaw rate controller. So that was also added to the C++ code. And now we could start writing some different maneuvers in Lua. So this was really exciting. I mean, for me to think that, you know, it was getting tantalizingly close at this point, and really it was. So we needed a way to pick a maneuver. So within the code, we could add a scripted item, have a command for which maneuver we were going to perform, and we could pass some arguments along with that maneuver. Things like for a roll, you might want to pass the roll rate and how much throttle you want to use, or the roll rate and maybe how many rolls you wanted to do. So we started off down those lines. We also discovered that we'd need some user parameters, and these were added over time, which gave a little bit more flexibility to performing these maneuvers. And of course, we needed to define the maneuver itself within the Lua script. And so that happened as well. And this is just some sample code for performing an axial roll. Now, those were our sort of starting steps, baby steps really, and scripted aerobatics was born. Now, Henry Wolfsberg has made some really exciting changes to that initial code. Not only has he done the documentation on the wiki page, but he's added tricks on a switch, which is just really, really cool, where you can define a switch on your radio transmitter and basically be flying along, flick a switch and do a roll or do a loop or whatever you define. And that's just a really cool development of this original idea. And just to show how simple things are, this is an example. I'm sure you're all familiar with Mission Planner and planning a mission. So between a couple of waypoints, we can add a script time item or command. We can tell a command ID, which our Lewis script interprets that as whether it's going to be a loop or a roll or some other maneuver you've defined. We can pass a timeout, which is important if things go wrong. We want control we want the mission to continue at some point rather than the script try to do something that it can't. And as I mentioned earlier, we can pass some arguments as well, things like roll rate or perhaps number of rolls. So that was all really exciting stuff. And of course, you know, with ArduPilot, one of the really powerful things is testing missions using SITL. And of course, we can do that with the aerobatics as well. So this was an early flight on SITL. This is using real flight to display the aircraft's flight path. So this is just a couple of minutes, and I'll just let this play. As I say, this is very early days. There's no navigation during the maneuvers, and that's something Matthew will talk about. So this is just a mission with some aerobatic script items between waypoints. And of course, once the Lewis script's written, adding these aerobatic maneuvers between waypoints is really simple, really easy. When anyone can do it, you need no programming skill at all. So this first maneuver was a Cuban 8. So it was a 5/8 loop with a half roll on the way down. Then a 3/4 loop, another half roll, and then exit. You can see the big jerk there at the end of that maneuver. That's the aircraft heading to the next mission waypoint, because again, here there's no path tracking during the actual maneuver. So this is a half Cuban 8 to come back. Maneuver familiar to anyone flying any basic aerobatics. And here we go with a slow roll. It looks like there was maybe a bit of building avoidance there, but really it was just the roll ending and the aircraft heading to the next mission waypoint. And that was just a loop. Right, so that was just really exciting stuff. And of course, after SITL, well, you've got to go and try it for real. Now, as I mentioned, I've really had very little experience with ArduPilot. So I thought a good model to start with would be a foamy, something cheap, simple, something I can fly at home and do some flights on. So the model I picked is probably not ideal, but anyway, it's an indoor EPP model. It's 36-inch span. It's got 3D control throws. It's got cheap, small servos. It's pretty unstable, and the trim's always different and all over the place. But nevertheless, I put a Matec H743 into it, a BN220 GPS, which doesn't have a compass. Also, I didn't put an airspeed sensor on the model. I did, though, put an ESP8266 to give some easy accessible telemetry so I could change things while I was flying and see what was going on. I found the 8266 in this model, because it's foamy, there's no sort of RF blocking bits, And with this plane, it was remarkable the range I got out of that back to my laptop. It's quite surprising. Anyway, so with this model, I went out and tried a roll. And this is really one of the first rolls. I was, reasonably high because I didn't really know what was going to happen. But through the mission, it came to the roll waypoint and did a roll. And I thought, wow, that was really cool. And a couple of weeks later, the roll became a rolling circle.
It was so cool to see that the first time. It's just amazing to see a real rolling circle on an aircraft actually working.
Look, it was, and it blew me away. And in fact, my wife was videoing it, and she couldn't quite believe it. That it just went along and did the whole thing itself, including the recovery at the end. Of course, that was early days, so rather than one roll for the whole circle, it was one and a bit rolls. But once it got back to the starting point, it sorted itself out, backed upright, and headed off to the next mission waypoint. So very cool stuff. So, but we always knew, this wasn't going to be the final solution. It was a really good start and really generated a lot of interest, but there was no navigation during maneuvers. And one of the big things about any sort of aerobatics is things must be wind corrected. And of course, there's no wind correction going on. And it was a bit like a blind pilot receiving aerobatic instruction over a radio link with lots of static. Like, it was probably going to get there and maybe the loop was going to happen, but we didn't quite know where it was going to finish. And we knew we were going to strike limitations with Euler angles. So, still had a lot to do. We still do have a lot to do. We're thinking about developing and adding quaternion navigation, and we also need a method for defining maneuvers. So Matthew Hampsey is going to continue. Matthew's a software engineer at a company called Seeing Machines, and he's a PhD student at ANU. He doesn't have any fixed wing experience, but he's got a lot of experience with drones. So he's been a huge help, and Matthew's now going to continue with some more technical bits and pieces.
Great. Thanks for that, Eddie. Hi, everyone. I'm currently dialing in from a tiny hotel room in Paris, so I might have some connectivity issues, and I do apologize if that happens. I'll also leave my video off, just not to incite the wrath of the internet gods. With the connection's not great. So I'm just going to be going over a couple of the technical details about how we, the next stages and how we ended up implementing this stuff in the Lua scripting front end. So I'll emphasize again, I'm a software engineer, not a fixed wing pilot. So there's a very good chance that I have some misconceptions about fixed wing flying. So if anyone sees those, please feel free to let me know. Cool. So just an overview of what I'll be going through. I'll look at how we want to define arbitrary trajectories for the fixed wing to follow. Some of the how we do the control on these trajectories, some of the issues we encountered when doing this path following due to our local attitude parameterization, and then how we fix some of these issues with a global attitude parameterization.
Oh, have we lost you?
Yeah, maybe.
Matthew? You're still there, Andy?
I am still here, yes.
All right, we'll give a few seconds, see if Matthew manages to reconnect. It was very kind of him. Unfortunately, he had a clash with a conference in Paris. He lives in Canberra, and so he was dialing in remotely from Paris. Just make sure that he knows. I'll send him. Sending him a message on Discord just in case he hasn't realized that he's disconnected.
Sorry, I'm back.
Welcome back.
Awesome.
It had the connection had been completely fine up until the point when I started mentioning that it had been spotty. Sorry about that. Cool. Sorry, which point did you guys lose me at?
We just finished this slide, I think, so probably next slide.
Oh, great. Perfect. Cool. So for the initial maneuvers that Andy and Tridge did, and you guys just saw some cool videos of that, most of these maneuvers were circular. And so it's possible to fly these trajectories by fixing a constant angular rate in one of the Euler angle parameters. And the value of that rate is determined by the radius of your circle. For example, if you're flying in a circle in the XY plane at some fixed height, you can fix a yaw rate of 360 degrees divided by the time over which that circle needs to be flown. And that will actually fly you in a circle. So that's what I mean by the terminology hard coding here, although that's probably not the correct phrase to use. What's a more correct phrase is that the rate is fixed for a particular maneuver. This approach does obviously not scale to arbitrary trajectories because the relationship I just mentioned is specific for circular arcs. So it's possible you can try and define all of your trajectories as piecewise circular arcs, but then you need to also insert a bunch of glue logic in between those, and it starts getting pretty difficult. So what would be much more flexible is if you can abstract out the trajectory into a function that maps you from time into some system state. And in fact, in dynamical systems, that's usually how you define a trajectory. Now, it is not immediately clear that this problem is actually any easier than the previous problem of defining your piecewise circular arcs. Because if you want to define the trajectory at each point in time, you now have to specify at a minimum a position, a velocity, an attitude, and angular rates, and all of those states and inputs have to satisfy your dynamical constraints of the system. So if this were a general dynamical system, at this point, you have to start pulling out things like trajectory optimization, which are really computationally heavy. It actually turns out to be a lot easier in practice because the fixed wing system is something that you call differentially flat. And what that means is you can actually specify a trajectory only in terms of position, and as long with a roll or a roll rate, and as long as that trajectory is smooth enough, you can infer all of the other system states at every point in time. So it shouldn't be too hard to convince you of this, because if you ignore wind, the fixed wing basically has to go in the direction in which it is pointing, right? So the velocity of the fixed wing somehow constrains the attitude, in that way. And in fact, it actually constrains all of the system states. So if you've worked with quadrotors, this should also be a familiar property there, although with quadrotors, it's actually the yaw, which is the flat attitude output. So there are some additional constraints on the trajectories that you need to enforce as well, such as making sure that the initial velocity is the same as the previous velocity, so you don't introduce any discontinuities. But that's what we do. And so as an example of that, here's how you might define a circle in this way, along with my artist's impression of a circle. And that works in practice. So if we could go to the next slide, please. Thank you. So these paths give us a position over time, and they allow us to infer a velocity, a set of Euler angles, and angle rate inputs from this. But of course, as with any real system, you end up straying from this defined path due to a variety of disturbances that get introduced. So we have to introduce stabilization along these paths. And we do this by introducing a Euclidean error in both the position and the attitude. And then we just use this error to feedback on the angle rate inputs. And we just use proportional feedback for that. So in fact, in practice, we actually end up relying on this feedback quite heavily, because everything that we've done so far has been model free, just because we don't, it's hard work coming up with a model. And so the parametric uncertainty that we're working with ends up being quite large. And so the feedback actually drives a lot of the path following. So in practice, this works in level flight, but flying aerobatics in a XY plane is not particularly exciting. So we also have to start looking at flying vertical trajectories. So if you go to the next slide, please. Okay, and so we need to fly vertically, and as we might expect, things start going wrong here, as anyone who has worked with Euler angles will tell you. So we define our vertical circle easily enough by just rotating the chunk of code we saw previously that defines the circle. And we threw that into the Lua script and tried to fly that, and it just didn't work. And so we dig into the code a little bit, and in hindsight, the problem is obvious. So ArduPilot uses a XYZ convention for Euler angles. And when we point directly along the Z-axis, we lose a degree of freedom. And basically what happens is roll and yaw become the same thing. And you can see that in these diagrams. And there's also a little video here, if we play that.
So how does Euler work? This Gimbal machine shows us. Each part is linked to one another. So when the parts slide around, we can see how the rotations are passed on. By spinning each of the machine's 3 arms, we can rotate the jet into any angle. But notice when the jet points up, our 2 of the circular arms match up. This is exactly the same effect of gimbal lock, causing 2 circular arms to rotate on the same plane.
Cool. And I just realized I forgot to credit that video. So my apologies for that. So ArduPilot in the back end maintains a global attitude representation. And so when we want to go from that global attitude to our local Euler angles, and we're pointing straight along the Z-axis, you have to pick a convention for how you want to split the angle between the roll and the yaw components. And there's no right choice here. And in the implementation, ArduPilot will basically switch between a -90 and a +90 degree roll angle, depending on the extent of rotation around the Z-axis. And so in effect, this introduces a discontinuity into the roll that we want to track, which just plays havoc when you want to track this. We really want these our error trajectories to be smooth. So there's a number of ways we can try and get around this. We can kind of try and patch it by implementing some logic to detect when we're pitching up and altering how we convert to the roll angle. But at the end of the day, this is not a robust solution. And this is really a fundamental mathematical limitation of using local coordinates, which are Euler angles here, to capture a global nonlinear phenomena, which is attitude. So if you go to the next slide, please. Cool. So I already mentioned ArduPilot already uses a global attitude representation on the back end. So why don't we just use this? So this is exactly what we do, but it does require some care. So a global attitude, which I've represented here with our rotation matrices R, it doesn't live in a vector space. It lives on what we call a group. In this particular case, it's the group SO3. And we need to choose an error that also lives in that group otherwise it's no longer physically meaningful. So the previous error we used, the Euclidean error, where we just subtract the current state from the desired state, no longer works, because if we subtract two rotation matrices, that's no longer a rotation matrix. And so what people will sometimes do in practice here is they will subtract the terms and then they'll project the resultant error back onto the group. So in this case, we could subtract two matrices and then re-orthogonalize the columns of the matrix and renormalize them to get a rotation element. But there is no reason that that this actually works, because you can significantly change the point at which you project down to. So that error is not really physically meaningful. But we can obtain a physically meaningful error by using group multiplication. So in this particular case, the error term that we want is the rotation that takes you from your current attitude to your desired attitude. And if we look at this diagram, and in this diagram, there is also a translational component just to emphasize that these are different transformations, because if they were pure rotations, they'd be on the same point, which would be a bit hard to see. So you can look at this diagram, and it's obvious that the rotation that takes you from R to RD, well, it's the rotation that takes you from R back to the inertial frame, that's R inverse, and then you multiply that by RD, and that takes you to your desired frame. So that is what our error rotation is. But of course, we need to go from that error rotation to a body rate, because that's the input into which we, that's the input by which we control the fixed wing. So a very smart guy called Euler showed a long time ago that every arbitrary composition of rotations corresponds to a rotation around a single fixed axis, along with a specified angle. And so we can extract that angle and axis from our error rotation, and then divide the angle by our time constant, and then remultiply those to get a body fixed angular velocity, omega. And we use that as the input into our controller. And so in practice, the particular representation that we end up choosing for our global attitude is quaternions, because they are convenient, because they only require 4 floats to store compared to 9 for a rotation matrix. ArduPilot already has a nice quaternion interface that we can use, and normalization ends up being a little bit easier. Cool, so next slide, please. Yeah, so unfortunately, I don't have a video to show you with this updated work in action, as it's still in early development, but that should be coming along shortly. And so some of the next steps that we're working on, we want to finish the current implementation, get it working robustly enough to put it on some real aircraft again, getting them to fly. For future work, we want the scripting interface to be robust and friendly enough for developers to start defining their own trajectories to be flown. And eventually we want pilots to be able to define their own 3D trajectories to be flown in some kind of CAD software, so that this stuff can still be used even if people aren't comfortable scripting. And for other future work, this is really in the far future. So we're doing a bunch of cool stuff with symmetries of dynamical systems over at the Systems Theory and Robotics Lab at ANU, which historically have been used for observer design, but we're also starting to look at control systems now. So we're super keen to start introducing that stuff into ArduPilot and getting you guys some cool stuff to use. That's it for me. Thanks.
Fantastic. Thank you, Matthew, and thank you, Andy. So it's been, such a privilege working with you two on this project. It's been absolutely brilliant, and really enjoyed our sessions on Discord that we've been working on this together. And just to give a bit of an idea, we've had a few discussions about how we might actually probably you can stop the screen sharing now, Andy, I think, so we can have. That's pretty better. Great. So we've been discussing a bit about what this eventually might look like as far as, how users might define their own trajectories. And at the moment, so Matthew and Andy and myself are sort of building the framework in the Lua scripts and in ArduPilot to allow us to fly an arbitrary trajectory. But we'll still need a way that non-programming end users can define that trajectory. And we've been thinking about something like being able to import a KML file or another, CAD format where you can sort of, and it'd be great if the tool that Andy showed at the start, where he shows that one where he's got a real mission and it just shows it with those ribbons, if that actually had an editing mode where it actually, edits a path and then is able to export it as a series of points, and then we load that at the start of the script, load that as off the micro SD card as a relative trajectory to fly. But we're very much open to ideas and suggestions on how we're going to define this, because that user interface is going to be really critical to the usability. Once we've got the maths right and it actually flies through trajectory really well, we'll want users to be able to create their ultimate sequence, the aerobatic sequence that they want to be able to fly, like that one that Andy showed right at the start. But how is the user going to define that? So suggestions would be very welcome. This is where somebody in the audience comes up with a great suggestion as to how we're going to do that.
Yeah, we're waiting with anticipation.
That's right. I mean, that's the whole point of this talk, to get somebody to suggest how we're going to solve that.
We're stuck.
So like one thing I'd say is with CAD programs, it'll be a little bit non-intuitive to actually draw that trajectory, because it's fair enough to draw the shape of where you want the aircraft to go, but it's when you want to start adding in aircraft attitude, like that is actually a really difficult shape to draw in CAD, which makes it a little tricky. But then I think if we were to write a little, some little applet that allows us to go from, you define where you want your aircraft to go, what state it's going to be in the next, X distance or X time step. So you can then define your aircraft's attitude and where its point in space is relative to that. And as long as it's got the GUI so you can directly see that, I think, that means each step in the path, the user only has to define 6 variables, and they would be variables that are very intuitive to them as pilots, roll pitch yaw, and then roughly the distance from the last time step as well. So I think it's probably the easiest way to do it is actually going to be something that's going to be a bit more custom than using predefined things. That's just what I would say. But I think the key step actually would be the fact that what we need it to do is convert or basically almost run like a mini simulation and compare to a param file for the aircraft it's going on to, so that we can compare the rate limits and acceleration limits to maximize the ability that the aircraft is actually going to be able to do what user has asked it to do.
Yes, with wind, there needs to be enough margin. So you'll have to define a wind limit when you're defining your path and say, I want to be able to fly this in up to 10 knots of wind. And, then it will have to work out, okay, well, if I've got a 10 knot wind, I'm going to need an extra bit of, oomph on this side of the path, some more acceleration, and is it going to be capable?
Yeah, totally. Yeah, very tricky problem.
Actually, I was just thinking that, pardon my voice, I'm going to have a lemsip after I finish here. I was thinking that, wind in the direction, or the trickier wind to assess would be a wind that's at 90 degrees to the line that's been flown. And that really requires, as a minimum, we would need a 3 degree of freedom, like a point mass model, where it's got some kinematic constraints to it in terms of its maneuver capacity, its ability to accelerate, and its speed range. But a simple 3-degree of freedom like Cartesian model would enable you to get 80% of the capture 80% of the wind limits. So I'm not quite sure though what's the easiest way for the user to define the actual trajectory itself. I mean, you've got CAD programs that can define that. In terms of the roll, are we just talking about wings level 45, 90 in each direction? But then how do we define something that's supposed to be a continuous roll?
We definitely we've got to have continuous roll. So yeah. I think, I mean, it's just a matter of how closely you space the points to start with.
Yeah.
I mean, we'll probably define the initial trajectories programmatically, but not necessarily programmatically inside ArduPilot. So we might, for example, have a Python script or a Java program or whatever your favorite language is, externally creating the set of points with sufficient data at each point to define the trajectory. And then we'd load that in some file format on the SD card, which then gets read and then interpolated.
Okay. Well, I mean, if we fitted if you fit a spline to a series of points, and so the user just dots the points in, you fit a spline to that, and we do have spline libraries already. You can get acceleration or spline libraries, but then you can superimpose the effect of the wind on top of that and probably just come up with an indication to the user, oh no, you've exceeded the ability of your aeroplane to accelerate or to turn or to, its speed, and just indicate to the user in red, oh, this is where you've exceeded it. And then it's up to them to modify the trajectory. Like, there's still a little bit of an art to it instead of a science, but if we can go from a trajectory the user would like to fly, and then giving the user feedback in terms of this is how much of the platform's capability you're using or how many Gs or speed you require relative to the platform's capabilities, then the human being can do what they're good at, which is, okay, I'm going to tweak the points, see what effect that has, and they'll quickly iterate in on a maneuver sequence they think they can fly.
Yeah, instead of showing them how much of the capability they're using, I think instead if you perhaps show them what it will actually fly based on the limits of the aircraft. So you'd have to put in the constraints, and then it would calculate not what you asked it to do, but what it will actually do. And then you see how much, if it's close enough, you're happy. If it's not close enough, you tweak the points.
Yeah, I mean, that's getting into sort of running the simulation, a simple simulation forward.
Yep.
As opposed to a spline, which in theory you could give them instantaneous feedback, as in color coded. Oh, it's gone red. I've exceeded the capability of my airframe with this turn. But then, of course, they need to understand what it is that they've got wrong. Did they was it unable to roll quickly enough to get into the required orientation, or couldn't it climb and compensate for the wind and keep a circular loop, or what is it?
Well, that's okay, I think, because that'll be part of sort of the art of creating these. I think there will be a creative element to creating these maneuvers, and people will sort of experiment and try with what it can do. It doesn't require a lot of really technical knowledge. It'll be very experimental, I think.
So, but the important is providing the user with rapid feedback, as in,
yes,
I've tried to make it fly this, but the plane's not going to be able to do it, so that they can sort of drag points or increase the radius. I'm not quite sure how we define this trajectory, whether it's a series of radii, and are we still talking points, or are we talking radii and straight lines like the old traditional aerobatic sequence elements? Or, I mean, I don't know where current aerobatics is at.
So, Andy, how, apart from the diagrams that you showed us, how are these maneuvers actually defined?
Well, they're defined using Aristi notation. So maybe, shall I just screen share and go back to my first slide, because I actually got an example of Aristi on that, just to bring that up. So on the left here, this is one of our aerobatic sequences. This isn't quite Aristi notation. Aristi is something used by the full size guys This almost is Aresti, but it's actually not quite. But anyway, that's by the by.
How do you spell Aresti? A-R...
Aresti.
Aresti, okay.
So the Aresti was a French aerobatic pilot that sort of developed the Aresti method of notation. You can imagine in a full-size aerobatic plane where you've got a complicated sequence that you probably really can't quite remember, and you're flying along and the plane's vibrating, and if you've got a maneuver name written down, you probably can't read it. But if you've got a picture of a maneuver, you can probably make out what that's supposed to be. So that was the idea behind it. And you can convey a lot of information in very quick shorthand. So this first maneuver here, so the circle defines the start of the maneuver, solid lines, upright flight. I'll only go through this one maneuver. So you come along, the arrow defines a roll, and it's a 3/4 roll. So this maneuver starts with a 3/4 roll, then there's a period of knife edge flight, and then the loop has actually got a roll integrated throughout the loop. So you start a knife edge, and as you start the loop, you also start rolling. So when you get to the top, you're in the opposite knife edge. So if you started knife edge with the canopy towards you here, by the time you get to the top, the belly of the plane's towards you. By the time you get back down to the bottom, the canopy's back towards you. Then there's a short period of knife edge flight, and then a 3/4 roll, and you actually 3/4 roll to invert it because it's a dashed line, and then on to the next maneuver, which starts inverted. So that's Aresti notation.
From that notation, Andy, what defines, say, how tight that loop is?
Well, nothing. So the pilot can choose. But in the sporting code, which is what describes the rules for competition aerobatic flying, we've got this maneuvering zone or box that in round figures is 300 meters high and 600 meters wide. The idea is to fill that aerobatic zone with the maneuvers. So the loop, that first maneuver is performed on center. So you can see that there's a group of maneuvers down the center of this diagram. So they are center maneuvers. And then the maneuvers to the right-hand side and to the left-hand side are called turnaround maneuvers that change your direction and bring you back towards center.
I guess, and the question I was thinking of was a lot of these maneuvers, things like your Cubans and things like that I'm seeing there, are the judges expecting like circular arcs? Like, are we still flying essentially circles and straight lines? Is that what makes up these maneuvers?
For sure. It's all straight lines, constant radiuses through various numbers of degrees, and rolls and part rolls, stall turns, snap rolls and spins, and that's about it. So it's very much defined components.
Okay. Yeah. So if you're defining a loop, you could really just have a parameter that says this is the starting altitude and this is the diameter, and you could tweak the diameter up, and at some point it will go out of your box, or your plane might not be able to do it, or there'll be some other limitation. But what I'm getting at is that we don't need to do arbitrary points to define things like loops, because that's a circle.
That's correct, as long as it's wind corrected.
Yeah. Yeah.
So one way is if we could have like a text version of this notation that, and we had an interpreter that displayed this diagram given the text, and the interpreter was also able to produce a path along with the derivative of the path and a roll rate at each point, then that would give us what we need.
I dare say we could do something like, you know how Simulink models are constructed, drag and drop boxes in like a flow chart. Mm-hmm. If we could take, end product, I'm thinking could be something like that, whereby we're just dragging and dropping this notation, and you've got, that your flow diagrams on the window on the left, and you've got basically what the interpretation of that looks like on the right. and each of those notations would then have to have a few parameters. So you could, I don't know, double click on it and then it pulls up a box. And for the loop, you could define what your max load factor on your aircraft wants to be. And that would scale how big your loop is in your box on the right. And so you get this sort of direct feedback of where that thing would be, what position in space. So it would be a format that would be very intuitive to people that, sort of likely to use this with that instant feedback of what shape that would draw in the sky as well.
Yeah, in fact, the Aerobatics catalog is available to well, I don't know if it's available to download. I was just going to have a look. Certainly available to purchase, which has got literally hundreds of maneuver components. And in fact, there's an online version where you can do exactly that as a full-size pilot. Drag and drop various maneuver components or maneuvers and build up a sequence.
Well, that sounds actually like a very hopeful way of doing it for these aerobatic. I've noticed there's a Wikipedia page about this, the Aerobatics catalog, and listing all the different notations and things. Interesting. Right, okay. So we just got to get the maths right to get it to actually follow these trajectories. So hopefully Matthew and Andy and myself will do a bit more work on this after the conference. And we'll probably initially do the sequences as functions in Lua, which is what we're doing at the moment, right? But there's no reason why that function can't then be broken out to be something that gets fed in from these Aerobatics sequences or a KML or whatever. We might even support multiple, inputs as long as it can, produce that path and define what the roll rate is at each point of the path.
Yeah.
Then you basically got the maneuver.
Yeah. Oh, and Twitch, tomorrow I'm talking. Part 2 of my talk is about the acceleration vector control.
Aha.
My first forays in it, which is not in an aerobatics application, but it's for more precise path following for conventional flight. But I can already see how that could, with extensions, some additional interfacing could provide some hooks in for more accurate aerobatics. So this is good.
Yes, fantastic. Thanks, Paul.
Yeah. I have a little bit of a question if we're getting to the generation of the maths sort of side of the problem. My couch is appearing in the background there. When we did multi-rotor quaternion attitude control, there was some interesting effects where so you can create you have an attitude that you want to get to, you have an attitude where you're at, we represented them both as quaternions, and you join the two together with a rotation. But there's a few things that are sort of tricky with that. Is one of them is that the shortest rotation isn't necessarily the sensible rotation for a given airframe. So for a multi-rotor, for example, we have a lot of roll and pitch authority, but little yaw authority. And we want to get our thrust vector to where it needs to be first and foremost, which will be similar to your lift vector. But yaw is, can get there whenever as it can. And so for a plane, I imagine you've got even a much more extreme situation where everything's relative to your velocity vector, well, actually your air speed vector, and you can only take a yaw offset to a certain, and a pitch offset to a certain extent past that. And so you can't just say, I want to be upside down right now, or I want to be like nose up right now, because you will have wing stall and all these sorts of things. So have you guys started to evolve your path planning between your current and desired attitudes to account for the dynamics of the airframe, so that you come up with sensible minimum path to remove your attitude error type things, or have you just done a simple, you've assumed that the error is small and within your capability of your airframe whenever you're doing that?
Leonard, with fixed wing aerobatics, I mean, I can only speak to this, but it's one of those cases where the journey is as important as the destination, as in it's how it looks transitioning from one orientation to the other. So there's a very specific sequence or thing that it's expected to do. So
yeah, I'm talking down at the 400 hertz level. So the actual, like we're talking about, like maybe I misunderstood what you were doing with the quaternion control. I thought you were saying you started to use quaternions so that you could actually go nose up and define a roll in the vertical, and to do that you required a quaternion attitude controller to actually be able to run through those maneuvers, as opposed to roll pitch Euler type axes. So in which case you were working on developing a quaternion attitude controller for plane, as opposed to the current roll pitch yaw style control.
Well, one of the things we're doing at the moment is the navigation control we're doing is actually only in 2 axes, even if it's a 3D path. So the navigation control is all using elevator and rudder. So we're basically doing body frame, pitch, and yaw. The roll is, the way I think of it, is the roll is to make it look pretty. And you want to be at this knife edge, you want to be upside down, whatever. So the roll is a property of where you want to be in the path, but the actual movement through space controlling your path, what we're just doing is elevator and rudder. And so it's more like, flying a missile sort of thing. You're going forward and you can either, move it up this way, move it that way. And then your roll is just to make it produce the effect, the visual effect you want, but not actually controlling your path with roll. Whereas normal navigation of fixed wing, roll is where it's at. When we're flying a pattern in fixed wing, we roll and then the roll produces our sort of turn rate. So it's all about the roll. But the roll is almost cosmetic in this aerobatics, which is sort of so different to the way we normally control a plane. Now, of course, I'm not an aerobatic pilot, so was that at all correct, Andy? Or
I think that's quite true. I mean, obviously, roll is used in maneuvers in its own right, like a horizontal roll or a 4-point roll.
Yes.
But during any other maneuver, like during a loop, it's simply wings level, and you need to just keep the wings level, and everything else is done with rudder and elevator for sure. And unless you are rolling, the ailerons are only used to keep the wings where they need to be, not to do anything else. Yep. All your path comes from elevator and rudder.
So you've only actually got 2 degrees of freedom to control your path. And so what we're doing in the maths is we're calculating a body frame pitch rate and yaw rate that we need to get back onto the path. And then we know we're going forward, right? Because we've got to keep going forward because we're trying to fly, actually fly the plane instead of, we're not yet thinking about the sort of stall turns and that sort of thing, which is going to be a whole other area to think about. Where you're no longer flying forward, you might be flying backwards or sideways or whatever. But we've just put that in the too hard basket for now.
S curves for plane.
Yeah, that's a whole new kettle of fish there. So my understanding was incorrect, that you're not actually redoing any of the attitude control for plane using a quaternion attitude controller structure. You're just looking to represent quaternions in your translation so that you can actually run through these full.
So the roll is entirely separable. We're using pitch and yaw to achieve a path, and then the roll to achieve an effect, but that is like a separated off completely. We want to be wings level, we want to be knife edge, we want to be rolling continuous, whatever we want to do, but that is entirely separate from the path we're trying to follow.
Yeah, and Randy makes a good point there in the chat that roll for the aeroplane is like yaw for the multi-rotor. you can fly multi-rotor around in a trajectory, horizontal trajectory, and yaw is entirely arbitrary. With the aeroplane, the roll is entirely arbitrary.
Right, but interestingly, in multicopters, typically yaw is the weakest
That's right.
axis in terms of rate.
Is the highest rate.
Right, exactly. Roll is you're giving up your strongest axis by far, right, for your path following. Your path following your two weak axes.
Yeah. And then the other thing is that you have a significant differential in acceleration in the direction of the wings. Is obviously you can generate about 4 times more acceleration perpendicular to the wings than you can at 90 degrees to that using the fuselage for lift, depending on the airplane, of course. So that's an asymmetry that would need to be taken account of in the maneuver sort of planning.
We've got a parameter for that in the aerobatic stuff where we say the ratio of the amount of lift you get, from knife edge versus level flight. And then we just apply that as a factor, as a sinusoid, to it. And that's how it does the axial rolls, and, it's bringing up and down the nose appropriately to keep you on track.
Yeah.
Yeah. Oh, this has been fascinating. We're a little bit over time now. Thank you so much, Matthew and Andy, for presenting that. It's been such a fantastic journey working with you guys, and also with Henry. The effort that Henry put in for the tricks on a stick, it's unfortunate this didn't work with the time zones to have, all 4 of us on the call at the same time. But just shout out to Henry for the great work he did creating the tricks on a switch, getting it out for end users on RC groups who are flying it, and documenting it. So